Hello everyone, in today's video we're going to talk about the applied optimization. So we have used derivative to help to find the maximum or minimum of some function given by the equation. But it is very unlikely that someone will simply just hand you the function and ask you to find its minimum or maximum. So most likely people will just describe the problem and ask you help in finding the maximum or minimum something, such as what is the largest volume, what is the greatest value, what is the cheapest way to do that, or what is the quickest way to get there from here. So in this section, we're going to discuss how to find this extreme value by using calculus. Here is the examples. So the manager of garden store wants to build a 600 square feet rectangular enclosure store's parking lot in order to display some equipment. This side of the enclosure will be built of redwood fence at a cost of $7 per running foot. The fourth side will be built of a cement blocks at a cost of $14 per running foot. Find the dimension of the least costly such enclosure. So for this story problem, there is some techniques. So the first step is you want to translate the English statement of the problem line by line or into a picture to visualize the problem, if that's applied, and or into math. That is often the hardest step. So now let's take a look. Well, a manager of a garden store wants to build a 600 square foot of rectangular enclosure. So this is rectangular and the square foot. The area is 600 square foot. And then three sides of the enclosure will be built of a redwood fence. And then the fourth side, let's say this one, it wants to be a cement. So that's why I use a different pattern. And I know the cost for the redwood fence is $7. So all of these three sides is $7. And the cement size is $14. So I enable these on my graph to help me understanding the questions. Oops. All right. So now, second is identify the object function and see the word looking for what is the smallest or the largest. So I need to identify the variable. And what they are looking for. So for this specific question, they are looking for what? They're looking for the dimension, right? Which will be the least costed dimension. So I write this down. I'm looking for the least costly dimension. Okay, so in our case, we have since this is rectangular, we have two dimensions, x and y. We can let the length equals to x and the width equals to y. Either way, it doesn't matter which one you decided because you end up to solve the same value. So if this is x, I'm going to label it on my graph x and y and y. Okay, so the next step is you need to know, okay, now we have two variables, right? It's a little bit hard to solve two variables on an optimized problem. So our next approach should be, how can I convert these two variables into one variable? Well, what you can do is find the constraint function, right? Constant function or equation. And then we can solve one variable into another variable. So what's the constraint? Well, the constraint is the area has to be 600 square foot. So that means x times y, the length times y, is equal to 600 is the constraint equation. So when I solve for y or x, either way, like I say, y is equal to 6 over x. So that means all the y can be represented by 6 over x. So the next step is you are trying to establish the function, the cost of the function, what the goal that you're trying to get. Okay. Oops, sorry. So we're looking for the cost. So we know that the cost is, we have 14x, all of this material adds up, plus 7y plus another 7x plus 7y. Because each fence cost, we already write it in here, right? If you have x feet long and each feet costs $14, so that means the total cost for that side, the cement side, is going to be $14. So that would be your total cost. Okay. So again, there are two variables. We want to substitute all the y equals to 600 divided by x into the function. So I have 6x plus 600 over x plus 7x plus 7 times 600 over x into the function. Okay, so now let's simplify it. So I will get 21x plus 18,400 over x. So that is my total cost function. And the next step is I am going to use the calculus to find the optimized value. Okay, so in our case, the total cost is equal to 21x plus 1800 over x. So why do we use the calculus? Because we know that at the critical points, the optimized value occurs. So that's why we need to look for the critical points for this function by setting the first derivative equals to 0. So let's find the derivative. The total cost, the derivative of total cost will be 21 plus 18.4 over x squared. Oh, no, should be subtract. Okay, so now we want to let the first derivative of total cost equals to 0. And then when I solve that, I have either x equals to 20 or x equals to negative 20. I'm going to skip the calculation here because I believe that you can do that by yourself. Okay, so we have 20 and negative 20. So in reality, we need to think about a reasonable domain for this question. So S represent the length, right? So can you have a negative number? No, so that means we have to cross the negative number. We just keep x equals to 20. So that means x equals to 20 is going to be the optimized, right? But we don't know, is it maximum or minimum? Well, how do you check if it's maximum or minimum? Well, we can use second derivative to check. F. So use second derivative to check, optimize, because we know that if it's concave down like that, we will have a maximum. If it's concave up like this one, we will have a minimum. So now let's find out the second derivative of the total cost function. So the second derivative is going to equals to 1688 over x to the cube. So when we substitute x equals to 20 for the second derivative, this is going to give you a positive number. That's enough. We don't even need to know the exact number, as long as we know y is positive, because maybe a fraction, but it doesn't matter, because a positive number divided by a positive number, you will end up to have a positive number. So this is positive, so that means at x equals to 20, the function is concave up, which means we will have a minimum at x equals to 20. Okay, so that's it. But now let's look back, see what do they ask. The question is ask you for the dimension. Now we only know the dimension of x. We still need to know the dimension of y. So since x times y equals to 600, so y is going to equal to 600 divided by 20, which is 13. So that means our one side, which is the side with salmon, is going to be 20 feet, and the other three sides is, we can say, so the length is 20 foot long, and the width is 13 feet. So in a word, that means the dimension of the enclosure that minimize the cost are going to be 20 feet times 20 feet by 30 feet. So this is a good example to show you how to use this step. We totally have 5 steps, right? You want to translate this into an English statement, and then the second step is you identify the variable, and then the third step is find the constraint function and try to use one variable to represent the other variable. And then the next step is you establish the equation for what they're asking you. And then the fifth step is you use the calculus to find the optimized value. The sixth step, it's not really a step, it's more like for checking, is to use second derivative to check, hey, if this is really the minimum or maximum or least, the greatest, they use different word to check if this is what you are looking for. So I'm going to show you another example. So here's another example to use the first derivative to find the optimization. So a concert promoter has found that if she sells tickets for $50 each, she can sell 1,200 tickets. But for each $5 she raises the price, 50 less people attend. What price should she sell the ticket at to maximize her revenue? Okay, so this one we can turn into a graph, but we can turn it into a math language. So now let's take a look. The revenue. Revenue equals to the price times how many tickets you sell, the quantity of the ticket, right? That's the revenue. Okay, so before the revenue, we need to know what is the price, what is the quantity. So we can let the price be our variable, P. So now we identify our variable. We use the P to represent the price. If you feel uncomfortable, you can still use X. I use P because the initial is P. Okay, so now we need to know quantity. We don't know, we can set another price quantity. Well, again, we can use the price to represent quantity. So let's read the sentences again. So when she sells $50 each, she can sell 1,200 tickets. but for each $5 she raises the price $15 less. Well, that sounds like a constant rate of change versus between the price and the quantity. So that means there is some linear relationship between them. So now let's list this one. If the price is $15, the quantity is going to be 1,200. And then if she raised $5, 15 ticket less. 15 less people attend. And then if this is 60, less, I'm sorry, should be 11.50. If she raised the price another $5, so that means another 15 less people attend. If we continue, okay, you can continue that. So now, as you can see, this is a linear relationship, right? So that means we can pick a random 2 points. I pick this one because this looks like the most whole number. So it's easier for me to calculate. I can find out, hey, what will be the relationship between Q, the quantity, times the price. We need to find the slope and the y-intercept, the vertical intercept. Okay, so since we have these 2 points, I can find the slope. Slope is equal to 1,200 minus 1,150 minus 60, which gives you -10. And then for the intercept, I need to substitute one of number into it. So I have 1,200 equals to -10 times 50 plus b. So b is equal to 1,700. So that means the price and the quantity we can write into a function as Q equals to -10 times the price plus 1,700. Okay, now since we can use P to represent Q, so that means we can go back to our revenue function. So now we can write down our revenue function as the price times the quantity, which we just found it is equals to -10p plus 1,700. Simplify it. I have -10p squared plus 17p. Now use our first derivative to find where is the critical point. So because the minimize or maximize is going to occur at the critical points. So, So this should be -20p plus 1,700. And I want this to be 0. So I solve t equals to 18.5. So that means when this equals to $18.5, we will have our extreme value. We still use our second derivative to check the function, which gives you -20. So -20 is always less than 0. So that means the function is going to be concave down at x equals to 18.5. So that means this is going to be a minimum. So that means the promoter will be able to maximize the, if it's concave down, it'll give you a maximum. Because concave down, going down, you will have a maximum. So in a word, you need to write in the sentences, the promoter will be able to maximize the revenue by charging 18.5 per ticket. And we can still calculate what will be the revenue or how many quantity she's going to sell. Let's find out all about that. So we know that the quantity equals to -10 times 18.5 plus 1,700, which is 815 tickets. And then the revenue is, we have equals to, we don't need to do the complicated one. We know the revenue is equal to the price times the quantity. So that means it's 18.5 times 850, which gives you 72,250. So That means the promoter will be able to maximize her revenue by charging $85 per ticket. At that price, she will sell 815 tickets and generate $72,215 in revenue. So I want to give you another important concept for this section. So the profit, sometimes we find out our maximum's revenue, but maximum's profit will be different than the revenue, because sometimes the marginal cost will be too big. So that means you might make no profit by making so much products, right? So here is our first concept in this class is the profits has the critical point, could be maximum or minimum, when the marginal revenue and the marginal cost are equal. So now let's do some recall. What is marginal cost and what is marginal revenue? So the marginal cost is equal to how much does it cost to produce one more items. So by the calculated definition, marginal cost is equals to the derivative of the total cost. And the marginal revenue is equals to the first derivative of the total revenue, or just the revenue. Price or quantity, sometimes they have different functions. So now let's see some examples. So a company sells Q ribbons binders per year at P prices per ribbon winder. The demand function for the ribbon winder is given. The price is equals to 300 minus 0.02 quantity. So the ribbon winder cost $13 a piece to manufacture, plus there are fixed costs for $9,000 per year. Find the quantity where the profit is maximized. Okay, so first of all, we identify the problem in the math word. So the profit should equals to the revenue minus the total cost, right? Okay, so revenue equals to what? Let's find our revenue, because they didn't give you a profit function straightforward. So that means we need to find the revenue function and the total cost function. So for revenue is equals to the price times the quantity that you sold. So it should be P times Q. And we know that there's some demand function, which is P is equal to 300 minus 0.02 times Q. So that means I can substitute our P with 300 minus 0.02 Q into our function. So I have a revenue function. Okay, So after I'm done with my revenue function, I still need to find out our total cost function. So the total cost function has two parts, the fixed cost plus the variable cost. So for the fixed cost is, they told you that, hey, each year the fixed cost is 9,000 and it's going to cost $13 to produce one. So that means the variable cost is going to be 13 times Q. So now I have our profit function. So our profit is going to equal to our revenue subtract the total cost. Sorry, this should be Q squared. After you simplify, I will get negative 0.02 Q squared plus 217 Q minus 9,000. Okay, so they want you to find the maximized profit. That means now we can use our first derivative to find the critical points. So the first derivative of the profit is equals to negative 0.04 times Q plus 270. And then we can solve for Q. When the whole function equals to 0, I will solve for Q equals to 6,050. So that means to maximize the profit, you want to produce 6,715 ribbon winders. Okay, is there another way to do it? Yes. So remember, we introduced a new concept here. The profit has its critical point when the marginal cost and the marginal revenue are equal. So our marginal cost and the marginal revenue, let's do marginal revenue. If it's equals to marginal cost, then we will have our critical points of the profit. So how do we get our marginal cost and marginal revenue? Well, by the definition, marginal revenue equals to the first derivative of the revenue. So our revenue function, what we did in here, is equal to 3,000 Q minus 0.02 Q squared. We set them equals to first derivative. Oh, sorry. So this is equals to 3,000 minus 0.4 Q. And now we still need our marginal cost. Marginal cost is equals to the first derivative of total cost. And earlier, our total cost is 9,000 plus 13 Q. So that means our total cost first derivative is equal to 13. So if you let these two equal, which is 3,000 minus 0.4 cubed equals to 13, you will end up to the same result, which is, oh, sorry, I write this wrong. This should be 300, not 3,000. Yeah, 3,300. So that means I want to have 300 minus 0.04 Q equals to 13. And when you solve it, I have a 27 equals to 0.4 Q, and divide by 0.04 on both sides, I have a Q equals to 6,050. So you should end up to have the same answer as you did by just taking the first derivative of the profit. Again, now we know that this is the critical point, but you're not sure that if this is a maximum or minimum. then I need to check. I still need to check. Use second derivative. So for the profit, second derivative, the first derivative is here. The second derivative is equals to negative 0.04, which is always less than 0. If it's a negative number, so that means this is going to be a concave down. If it's concave down, that means it reaches its maximum profit at when they produce or manufacture 6,715 ribbons. Okay, another business concept is the average cost. Sometimes they want you to find the minimum of the average cost. So what is average cost? So by definition, average cost has critical points when the average cost and marginal costs are equal. So now I'm going to show you an example. So here we are. The cost in dollar to produce Q gift basket is given by this and this, and then find the quantity where the average cost is minimum. So the average cost and the marginal cost, when they equal, then we will have the critical point, which is this equals to be a minimum. So the first thing is we need to find the marginal cost and the average cost. So the average cost is equals to the total cost. Since it's average, we use the total cost divided by the quantity. In our case, it's given the total cost is 160 plus 2Q plus Q squared divided by Q. So when you simplify, I have 160Q plus 2 plus Q. That would be your average cost. And then what is the marginal cost? Well, the marginal cost is equals to the first derivative of the total cost, right? So that means I want to take the first derivative of the total cost, which is 160 plus 2Q plus Q squared and first derivative. This equals to 2 plus 2Q. So now we have average cost and the marginal cost. So that means when these two is equal, we will find our minimum average cost. Okay, so the average cost is this plus, not plus, equals 2 plus 2Q. Well, when we simplify it, I have a 2 and subtract 1Q. So I will have 160 over Q equals to Q. So that means 160 equals to Q squared. When you take take square root, I have either Q equals to 40 or Q equals to negative 40. Again, for reasonable domain, we know that you can produce negative amount of gift basket. So that means we should only leave the Q equals to 40. So that means when you produce 14 baskets, we will have our minimum average cost. We can also check if this is correct. So to find the average cost, we know that, hey, our average cost function is here. So now the first derivative of average cost function is equals to 160Q plus 2 plus Q first derivative. This equals to negative 160 Q squared plus 1, and then second derivative. Second derivative should equal to positive 160 times 2 over q to the cubic power over q to the cubic power. So that means when you input a positive number, which is when I put q equals to 14, 14 to the cubic power is always a positive number, right? So that means at second derivative at q equals to 14 is always concave up. If it's concave up, that means we will have our minimum. Okay, so that means we will have the lowest average cost when we produce 14 gift basket. So that's it for today's classes. So today we all have these storytelling questions, problems. So the key word is, like I said earlier, we need to identify that either draw a graph or turn into the math word, such as what equation that we're going to use, and then follow this step by step. You should be able to do it. Okay, I'll see you in next video.